Happy Thursday, everybody. We are only about a week and a half away from the end of school. So remember, there's no quiz today, obviously. Just as a review of where we're at here, we were talking about, Chapter 6 is on lengths, areas, and volumes, and we started with areas. Now we're talking about volumes, and we've got volumes, and we're actually going to be doing volumes in two different ways. One is using what we're calling the slice method, and the other is using what we're calling the shell method, and we're going to get to the shell method next Monday. Again, just as a review of our schedule, Monday we're talking about shell method. Wednesday I'll go through some review. I'll go through kind of a review of here's what I expect you to know. Generally, here are some good things to study. Those review problems were passed out yesterday, but you're welcome to start looking at them now if you'd like. Again, my advice, I'm not going to grade you for completion on those review problems. I only want you to look at the review problems that you feel like are going to help you. The answers are posted on RedWeb, so the point is not to get the answer, but the point is to remember how to do these problems. So make sure you're studying that way. We'll go over what kind of the general thing is, what I'm expecting you to know from all of the material. And then on Thursday, I'll physically be there to answer any review questions you have, any will this be on the exam or not type questions, as well as go through one last section. That'll be our last day of lecture. So that'll be next week. So just to review, let's review by doing a one more slice method problem here. So let's take the region bounded by the functions y equals 2 minus x squared and y equals 1, and we're going to rotate that. So this is going to be rotated around the axis y equals -1. Okay? So we have a region bounded by these particular functions, 2 minus x squared and y equals 1, rotated around the axis y equals -1. So let's start. Again, we start by always drawing our region. So 2 minus x squared, if you remember, x squared looks like this, negative x squared looks like this, and then we go up 2. So here's our 2 minus x squared. And then y equals 1 is right here. So our region that we're interested in is right there. And the axis that we're rotating around is this axis right here, y equals -1. We've actually used these two functions before. They intersected -1 and 1. So what we're going to do now is we're going to draw this region rotated around this axis. So let's do that here. Okay, so first we're just going to draw the region from -1 to 1. That's the region. And then the axis is here at y equals -1. So make sure when you draw, what the next step is, we're going to draw the region rotated. We want to draw it rotated 180 degrees. You need to think about where is this region going to be. There's 2 units between the bottom of this region and the axis. So down here, there had better also be 2 units between the region and the axis y equals -1 there, okay? Okay, so that's the bottom. That doesn't look great, but it's okay. That's the bottom of that. So we've got this shape, and then 2 kind of units here, and then 2 more units in that shape. And when we rotate, what's going to happen is we're going to get something that looks a little bit. This part's going to rotate in a circle. This part's going to rotate in a circle. That's behind, so that's why I'm drawing it dotted. It's going to look a little bit like a napkin ring. Okay? And now what we're going to do is we're going to slice this original part here, which would be a slice up here. And if we rotated that slice would also show up down here. And the rotation of that would look something like this. Right? So in other words, kind of hard, maybe I put too many lines in here, it might be a little hard to see. But that is what we call a washer or an annulus. Okay? So we've got our region, the volume, and then we drew a sample slice so we kind of know what that slice looks like. And then the way that we set up our integral is going to be set up as the overall volume is going to be the sum of the volumes of these slices. And the slices are an area across times a thickness. Right? And in this case, the thickness is dx. And because this section is an annulus, the area of the annulus is going to be the area of the big circle minus the area of the small circle. So it's going to be the area of the big circle minus the area of the small circle. All right. So now the area of the big circle is going to be pi times the radius, pi times the big radius squared. Hoping you can see that. The area of the small circle is going to be pi times the small radius squared. Let me see if I can switch to blue here. Just don't want that to be so faint that you can't see it. Let's see if my blue will last. And x goes from -1 to 1 here. So let's stick that in there. All right. So all we have left now is to figure out what this big radius and the small radius are. Now the big radius is from the axis up to the top function, so that big radius is right there. Now, this height right here is the top function, which is 2 minus x squared. That distance right there is 2 minus x squared. But that's not the radius. The radius is that function plus another 1 unit, right? Because if the axis were the x-axis, then the function would actually be the radius. But since the axis is down here, another 1 unit, we have to add on another 1. So the big radius is the top function, 2 minus x squared, with another 1 added on. And then the small radius, is the bottom function with another 1 added on. Right? This is the small radius. Small radius is right there, which is right here. And that function is 1 with another 1 added on. So that's 1 plus 1. So in other words, the integral we need to solve is the integral from -1 to 1 of pi times 3 minus x squared, quantity squared, minus 2. 1 plus 1 is 2 squared is 4 pi. Does that make sense on the setup of that? Again, I'm not going to multiply that out and work it out because it's not worth our time right now. But the key thing here is that when we're working, we have to first recognize what is this area that we're working with. In this case, it was a washer. So we have to take pi times the big radius squared minus pi times the little radius squared. We have to go back to our picture to figure out what is that big radius and what is that small radius. Okay? So hopefully that makes sense. What we're going to do now is just a couple of examples where we're not going in the x direction, but instead we're going in the y direction. So let's try that here. Okay. Okay, so let's take a look. Let's have the region bounded by y equals x equals y squared, x equals 0, y equals 2, and then let's rotate that around the y-axis. Okay, the region bounded by x equals y squared, x equals 0 and y equals 2 rotated around the y-axis. So let's first draw our region here. So here's x equals y squared. It's kind of like y equals x squared, but flipped. Okay. Here's x equals 0 is the y-axis. And then y equals 2 is up here. 1, 2. Okay, so this is the region that we're interested in. And we're going to take that region and rotate it around the y-axis. So you can see we're not doing the x-axis this time, we're doing the y-axis. So when we do that y-axis, what's going to happen so the original region looks kind of like this. So we're just going to redraw that over here. 1, 2, 3, 4. It's because, again, we're rotating around the y-axis, so I'm taking this and flipping it around on the other side, a mirror image of it. Okay. And then, so then when I rotate that, this is actually going to look like a circle. So let me draw a little circle like that. So it'll look, again, kind of like a cone, but a pinched cone, so it's pinched down at the bottom there. Let's draw in a little slice. Now I mentioned that we're switching to y direction instead of x direction. So if you imagine slicing this, if you wanted to slice it so all the sections looked like the same shape, you wouldn't want, if you slice it like this, things would look crazy and you wouldn't always have the same shape. If you slice this way, you would always have the same shape, and that shape is going to turn out to be a circle. So if you slice this way, and you were to take that slice, wish I had a working black marker here, and rotate it, all right, hopefully you can kind of see a little bit of this at least. That ends up looking like a circle. Yeah, it's died. Let me try green and see if that'll show up. Okay. All right, so to get the volume now, this is bad. To get the volume, I need to add up these slices, which means I need to add up area times thickness. And in this case, my thickness is dy. So y is going to go from 0 to 2, like we had mentioned before. And this region that we're looking at is a circle, so we're going to, the area of a circle is pi times the radius squared and in this case the radius is this function right here, x equals y squared. We're thinking of everything in terms of y now. So the radius is y squared. So the integral that you need to do is y to the fourth. Okay, does that make sense? dy. And since we're so close, let's go ahead and do it. It's going to be 1/5 y to the fifth from 0 to 2, and if you plug in 2, you get 32 pi over 5. That's going to be that volume of that region right there. All right. Hopefully that makes sense. Let's try another example here. Let's do the region bounded by the function x equals y cubed just rethink this just for a second. So let's do y equals x to the 2/3. Sorry. I'm rethinking this as I'm doing it. Okay. Let's go back. Let's do x equals y cubed, x equals y, but x has to be bigger than or equal to 0. So I want the region bounded by those things. And then let's rotate. Let's have that rotated around the line x equals -1. Okay. So let's first draw this. X equals y cubed looks like y equals x cubed. Rotated, so instead of being your disco man this way, it looks like this. Okay. X equals y looks like this. Y equals x. And I want x bigger than or equal to 0. So I only want this region here. Just take that region there. I don't want this other region. Okay? So I want x equals y cubed, x equals y, and then just this upper part. So don't consider this region down. Right? So that's the region we want. And we're going to rotate around x equals -1. So we're going to rotate around this axis right here. So we're going to take this and rotate it around that axis. X equals -1. Are you with me so far? So let's do that now. Let's take that region. Okay, we're going to redraw the region here. Okay, there's the region. And here's the axis, x equals -1. Now make sure when you redraw this, don't draw it right here because it has to be like there's a mirror right here. If there's a unit space here, there has to be a unit space there. Many times I see students, they don't think about this being the mirror. They kind of just draw something and throw this over here. If there's a unit space here, there's got to be a unit space there. So if I'm mirroring this, it's going to sit over here, right? And then if I'm rotating that around the axis, that's going to create circles up here and circle down there, right? So that's going to look kind of like a bowl but the insides are kind of slumped out, and it's flat on the outside, and I can reach my hand through. So it's kind of like a weird funnel or something like that, right? And if I were to slice it, there's a couple different ways I could do this. I could slice it vertically, but we're looking at these from a slicing this the other way. So what I'm going to do is I'm going to slice it this way since everything's in terms of y. So if I slice over here and rotate, what I get is, again, what we were getting before. We get an annulus, right? Kind of see that? See that green thing? So if I pull it out, that's an annulus right there. Okay? All right, so now to get the volume of this, right, so it's going to be area times thickness. Again, the way that we're slicing this, the thickness ends up being dy, and y goes from 0 up to this intersection point right there is y equals 1, so from 0 to 1. And because this is a washer, the area is going to be pi times the big radius squared minus pi times the little radius squared. All right. So we just have to figure out what is that big radius and what is that little radius. So that big radius, which is right here, is this length right here. And that is the original function, this upper function here, y, but then we're adding on an extra section here. Here's y, and here's this extra section. That extra section is 1, so that big radius is going to be y plus 1. And that's what we're squaring. Okay, the little radius is right there, which is the bottom of this thing. If I have my head tilted this way, the bottom function is y cubed, so this is going to be y cubed plus 1. So the smaller radius is going to be y cubed plus 1 quantity squared. It's super critical that you're following how we're getting these set up. The actual doing of those integrals, I can trust that you can multiply those integrals out and do them. But it's getting the fact that this is the large radius, which is y plus 1. This is the small radius right here, which is y cubed plus 1. Right? Again, making sure that your pictures are accurate is going to help you immensely. Okay, let's look at one more example. All right. Okay, so we're going to take, for example, we're going to take the region bounded by y equals x, y equals x, y equals 0, y equals 4, and x equals 6. and we're going to rotate this around the axis x equals 6. Right? This is like the last homework problem on section 6.2 when you eventually get to that. All right. Okay, so first, again, let's draw this region. So we've got y equals x, y equals 0, which is that x-axis, y equals 4, 1, 2, 3, 4. That's this part. And x equals 6. So 1, 2, 3, 4, which is where that is. 5, 6. So this is the line right here. So what they want is this region right here. That's the region bounded by all 4 of those together at the same time. That's the region we want, and we're going to rotate that around x equals 6. Now, let's go ahead and do that here. Actually, I don't need that part left of the axis, so let's... Okay, so 1, 2, 3, 4, 5, 6. Here's our axis that we're rotating around. 1, 2, 3, 4, 5, 6. We should have some symmetry there. So we're going to go up 4. So we're going to have a line right there, and then this is going to be flat right here. So our region looks like that. And therefore our other region is going to go over 2, and then go down in a straight line like that. Okay? And if we're rotating this side over, it's going to look like this. Like an elephant drum, kind of. Okay? And the question you need to ask yourself in order to figure out, should we slice vertically, should we slice horizontally, is if you were to take this and slice it in a meat slicer, if you slice it this way, will all the things look the same? Or if you slice it this way, will they all look the same? And in this case, what you want to do is slice it this way, and if you slice it this way, they would all look like what? Let's try that here. So if I were to slice this horizontally this way, then come over here and spin that, what you would get is a circle. Okay? And we just have to figure out the radius. Okay. Everybody in agreement? Does all make sense? Okay. So our volume now is going to be the sum of our areas times thickness. Okay, and usually when you're doing these, when you have x versus y and it's not clear, start with the thickness. The thickness here is dy. So everything is going to be in terms of y here. Okay, so our thickness is dy. So our limits are going to be in terms of y. Y is going to go from 0 up to the upper region. This thing ranges from 0 up to 4. So we're going to have limits from 0 to 4. And the kind of area that we're looking at, it's a circle, so the area is going to be pi times the radius squared, right? Everybody with me so far? So the thickness is dy, like delta y. Y is going to go from 0 to 4, and this is a circle, so we want pi times the radius. All right. Now we just have to figure out what this radius is. In other words, what's this length? Now this is where you have to be a little bit careful. This line right here is the line x equals y. but the length of y, at 0 the length is 0, and at 4 the length is 4. So that x equals y is actually this length right here. This overall length from the y-axis to the axis of rotation is 6, right? This is x equals 6. So therefore, how long, or my screensaver kicked in here. How long is the radius? The radius is right here. This is 6, and this is y. So the radius right there is 6 minus y. This thing right here is 6 minus y. So what I want to do over here in my integral is I'm going to have the integral from 0 to 4 of pi times 6 minus y quantity squared. Okay, because that's that radius right there. Right? So 6 minus y is my radius, and that's what I want to square. Okay? And then, again, you would square this out in order to actually do the integral. And I'm not going to, you need to do that on your homework, but I'm not going to take the time to do that here. Right? Okay. Hopefully that makes sense. What I want to do now is just a couple of, you have a couple of formulas that you've seen before in terms of volume, but you've never seen them proven before. So I want to take a few minutes here at the end of this section and just prove to you a couple of formulas that you've seen before. One of those formulas is the volume of a... Yeah, that has completely died. I found this one. Let's see if this works. Ah, yay. Okay, the volume of a sphere. Do you remember the volume of a sphere? It is 4/3 pi times the radius cubed. So let's see if we can get that from the from using our methods here. All right? Okay, so what we're going to, in order to get a sphere, what we're going to do is we're going to take our typical circle of radius r, and we're going to rotate that. Let's do the top half of the circle. So we take this top half of the circle. Remember, the formula for the top half of the circle is y equals the square root of r squared minus x squared. We would take that and rotate that around the y-axis, and that would give us our sphere over here. So let's do that. If I rotated that down here, it should line up. Okay, and so we're going to take, it actually doesn't matter if you slice it this way or if you slice it this way. Let's slice it in the x direction, because I think you feel comfortable, more comfortable with that. So if we were to slice this here, that would look like a slice over here, rotated, okay, it would be a circle here, right? All right, and this is going to go from negative r to r. So our volume here is going to be area of each section times the thickness. The thickness is dx here, right? Dx, delta x. All right, and our area, well, x is going to go from negative r to r, so let's fill that in. And the area is pi times the radius squared, because it's a circle. This disk down here is a circle. So it's pi times the radius squared, and the radius, which is this thing, which is this thing, which is this thing, is the height of the function. So we're just going to stick that function in. square root of r squared minus x squared squared. Okay, follow so far? Radius is just this piece, which is this piece, which is our function. So this is actually nicer than when we did the original circle because the square root gets squared. So this is actually a much nicer integral. Let's pull that pi out. And then you're looking at r squared minus x squared. Now we're integrating that with respect to x. So r squared is a constant. Think of that as like 25. So if I were to integrate 25 with respect to x, I would get 25x. So don't make that r 1/3 r cubed. You're integrating with respect to x, so that's going to be r squared, whatever that number is, times x, minus the integral of x squared is going to be 1/3 x cubed. Okay? The key here is to remember what's a constant and what's not. R is a constant here. So don't get confused by that. Okay, if I were to fill in, let's put in r first. So putting in r, I get r cubed minus 1/3 r cubed minus, here I get negative r cubed plus 1/3 r cubed. You probably see where this is going. I've got a whole r cubed minus 1/3 of an r cubed gives me 2/3 of an r cubed. Over here, I get negative 2/3 of an r cubed, but I've got another negative, so that's plus another 2/3 r cubed, which gives me 4/3 pi r cubed. Okay? Make sense? So that's our volume of a sphere. Nice. Okay. The other one that I want to do for you is the volume of a cone. All right, the volume of a cone. Oh, no. Come on. Volume of a cone. Now, typically when you have a cone, you talk about a radius of the cone, r, and a height of the cone, h. So that's what we're going to need to refer to here. And if we do this, right, then the volume of a cone is usually, it's 1/3 of the base, which is pi r squared, times the height. That's the volume formula that you've memorized in the past. What we want to try to do here is actually figure out why that works. So here's what we're going to do. We first have to figure out what region are we going to rotate and where are we going to rotate it. So we probably want to rotate a triangle here around the y-axis. So we first have to get a formula. If this is height h, and this goes from 0 to r, what is the formula for this line? Okay. Well, it's a line with the y-intercept is h, so it's going to be something x plus h, because the y-intercept is h. And the slope is going to be, we go down, remember it's rise over run, so we're going to go down h and over r. So the slope is going to be negative h over r. Notice that if I were to plug in x equals r, the r's cancel and I get negative h plus h gives me 0, and that's where this is. So that's a good sign. So that's the formula for that line. So what we're going to do now is we're going to rotate that around the y-axis. When we do that, we get something over here, and we're rotating around the y-axis, so it looks a little bit like this. That's our cone that we were expecting. And the question we have to ask ourselves now is, how are we going to slice it? Are we going to slice it like this? Or are we going to slice it like this? Probably what you would expect is for us to slice it like this. If you slice it, you can do it like this, and you get triangles. We're going to slice it like this and get circles, okay? So we're going to slice like this, which means we're also, so we're going to see something over here. And the resulting thing that we get ends up looking like a circle. All right? So for the volume here, the volume is going to be the sum of the areas times the thickness. All right? So we always start with the thickness because it's easiest to see what the thickness is. Y, it's dy. So let's put that in there. And then we have to ask ourselves, where is y going from? Well, it's going from 0 to h. So let's put that in from 0 to h. And then this type of area, it's a circle, so we're going to have pi times the radius squared. Okay? So pi times the radius squared. Now we just have to figure out what that radius is. Well, we're integrating with respect to y, so the radius is this function, but we need the function in terms of y, not in terms of x. So we're going to need to solve this for y. So let's take this over here, and let's solve for x here. So we're going to take y, and we're going to subtract h. Okay. Then we're going to multiply through by negative r. Okay, if we multiply through by negative r, that gets rid of the negative and the r here. I get negative ry plus rh. Then what's left over here is hx. So now let's divide by h. So x equals negative r over h y divided by h. So that's plus r. So this is our radius. That's what we're going to stick in here. Right, the integral from 0 to h of pi times negative r over h y plus r. Right? So our integral is set up. It's just the pi times the radius squared, and we had to solve for y because everything's in terms of y. So now let's pull the pi out, and let's multiply this out here. Okay? We've got negative r over hy plus r times negative r over hy plus r. So we're going to get, if we multiply that out, we're going to get r squared over h squared y squared. That's the first term. We're going to FOIL. The outer and the inner are the same kind of terms, so we're going to get two of those. So we're going to get minus 2 of, we've got several r's, so we're going to have an r squared over h times y. And then r times r is going to give us a plus r squared. Follow me so far? All right. Now remember, everything in here is a constant. This is a constant. This is a constant. R is fixed and H is fixed. All of this stuff, all of these are constants. The only thing that's not constant is this y squared and this y. So when we integrate with respect to y, remember, all of this stuff is just constants, so it just comes along for the ride. Okay? So we just rewrite r squared over h squared. Like if that was 24, you would just write 24 there. And then the integral of y squared is 1/3 y cubed. Okay. Minus 2r squared over h, and then the integral of y is 1/2 y squared. Plus, r squared is just a constant, so if that was 24, we would write 24, and then our variable that we're integrating against is y, so 24y. And we're going from 0 to h. Okay? All right, we're very close now. Notice when I plug in 0, everything's going to go to 0, so I don't have to worry about the 0 part. When I plug in h, what happens? We get r squared over h squared, and then 1/3 h cubed, minus the 2 and the half are going to cancel. I get r squared over h times h squared plus r squared times h. Well, one thing that you'll notice is that the h's an h cancels here, and I've got an r squared h and a negative r squared h. So these actually go away. And I've got 3 h's here and 2 down here, so those cancel, and what I end up getting is 1/3 pi radius squared times my height. Lo and behold, that is the volume of a cone. All right? Wow. Well, you did it. You figured out the volume of a cone. Now, one other thing I want to point out here that's very, very interesting is that it actually doesn't matter whether this cone is upright or if this cone was like this, but had the same height. If it's a slanted cone or an upright cone, these two cones have the same volume. And the easy way to think about that is that if you sliced this cone up and just took your hand, so slice it up like a bunch of pieces of salami, and then you took your hand and shoved it over, you didn't change the volume, you just changed where the slices were. You would get this figure over here. If you imagine slicing this up and shoving all the salami pieces into one, so they're upright, it would look like this. So these two things actually have the same volume. And the easy proof for it is using the slice method. Kind of visually just thinking about slicing this one up and slicing this one up, you get exactly the same. Volume in both of those contexts. So slanted figures, all you care about is the height and the base, not necessarily what the angle of slant is. That doesn't come into it at all, which is another really cool thing that you can get from the slice method here. All right? Okay, so I hope you all have a great weekend, and we will connect on Monday to look at one more volume method that's called the shell method. And then Wednesday we'll go over, we'll do some review of material for the final exam. So have a great weekend, everybody.